I'm doing the ladder problem. This is my model right here. You can point to the model. So I have markers here. It shows that it's, well, first of all, the chair is 44 inches tall, and then as it's leaning, it stands at 39 inches, and then it's standing 20 inches away from the wall. Okay, so now I'm just gonna pull it, make sure everything's in frame. Okay. Okay, so from the video, we know that the chair is 44 inches long, and top of the ladder from the ground is 39 inches, and then the foot of the ladder from the base, that's gonna be 20 inches. All right, so we can just draw a model of what we had outside. So I'm gonna use the variables z, x, and y. Okay, so then we know that z is the length of the chair, which is 44 inches. And then we know that down here, the base, x is 20 inches. And then we know that the top of that from the ground, which is just the height right here, so that's equal to 39 inches. Okay, so now that we have all this, we need an equation that represents this, and then we know that it's a right triangle, so we can use Pythagorean theorem, which is a squared plus b squared equals c squared, but in this case we're just going to use these variables, so we can use x squared plus y squared equals z squared. And we just write a side note, right? Actually, no, we already have what each of these values are equal to. So what we're gonna need to do is, also from the video, I'll show a clip right now. All right, so this is the video of it sliding, and every point, the bigger markers that have something written underneath it, you can't really see it from here, but everyone is separated by 5, and right now the bottom of the chair is at 20 inches. So the inches I chose were, so that's at 5 currently, but I went all the way to 10 inches. So that's the second line right there. So as we see right there, right when it's at 10, or right when it's moved to 10 inches, it does that at 51 seconds. We see that at the bottom left right there. So we used 10 inches over 51 seconds. We know that the rate of x, as the rate of which it's moving, is dx over dt, and that's equal to 20 inches per second. Okay, and then basically how we got that is that in the video we saw that it was moving, it moved 10 inches at 0.5 seconds. So we can just do 10 over 0.5, that's inches, and it's seconds for the bottom, and that's equals to what we have right here, 20 inches per second. Okay, so now all we have to do is differentiate this so we can do it in respect to time. So that's d over dt, and then so x squared, so this is in respect to time, we're gonna do chain rule right here, so it's gonna be 2x times dx over dt, and then it's gonna be plus, same thing right here, 2y dy over dt, and then z is just a constant because it's the length of the chair, so it's gonna be, when you differentiate that, or when you, the part of that is just basically 0. Okay, and then from here we can just plug in, or first of all we can just get rid of the 2, we can just divide 2 from each side, so we can just cross that out, and then we can just plug in the values we have here. So we know that x is equal to 20, so we can plug in 20 right here, and then dx over dt is also 20, so 20 times 20, and then plus y, we know that is 39, plus 39, and we don't know the value of dy dt, so we're gonna leave that here. So now what we can do is multiply 20 by 20, and that is 400, and then we'll move it to the other side. So it's gonna be, I'm just gonna flip it around here. So we'll keep 400 on this side. It's actually negative because we moved it to the other side by subtracting. So negative 400 is equal to 39 dy dt. Okay, and then from here we just divide 39 to the other side. So it's negative 400 over 39. And let me just grab my calculator 1 second. Okay, so then when we divide negative 400 over 39, let's see, negative 400 over 39, we're gonna get negative 10.25. We'll just run it to negative 2 point. We'll run it to this, negative 10.256. Okay, so then that is also our dy over dt. So from this equation that we have right here, the data and information we have here, we find that the rate at which this is falling is negative 10.256. And then now we just have to compare it to what it actually is in the video. Okay, so this video shows us the markers of the height. So in here we're able to calculate the rate at which it's moving when it's sliding down the top of the chair. So I chose to measure it at when it lost 6 inches. So on the left you can see that there's markers for in fives, like 5 inches, like differences of 5 inches, but I just chose to do threes because it starts from 39, and I just thought it'd be easier. So we see that it starts at 39 inches in height, and then I chose to do it when it lost 6 inches. So at this point, it's only lost 3/8 at 36, around there. But when it goes down to, when it loses 6 inches, we can see that it loses 6 inches at 0.51 seconds. So what we'll need to do now is divide negative 6 over 0.51. Let me go back to that just to show you. At the bottom left, it shows that. Okay, so after watching the video, we saw that once it moved down 6 inches, the time that it did that was at 0.51 seconds. So then when you divide negative 6 by 0.51, we get, well, we can just round it to negative 11.768. So you can also write equal to dy dt. So this is the real answer according to the video, and this is the answer we have according to all this information and the rate we got from the video of x moving. So when we compare the answer we got from our calculations and then the actual answer from the video, we can see that the difference between the two is 1.52. So that's the difference between them. It's pretty close, but there's reasons why it's not fully accurate. I would just to restate the answer for the rate of y as it goes down the wall. The answer we got from the calculations was negative 10.256 inches per second. And then the actual rate that we got from the video was negative 11.768. And then I just wanted to go over the reasons why the answers aren't the same. They're inaccurate. Although they're pretty close, there's little things that gets in the way of that. Like the first thing, that the measurements, they're not precise. So I put the markers down and I just slowed down the video as much as I could to find the rate of x as it moved along the floor. But the video can only capture so many frames. It's impossible to get the exact rate from that. So there's that. And also, to add on to that for number 2, the ground isn't smooth. Like, it could have could have been pulled at a different rate because of like how bumpy the floor could have been. It's not as perfect as like the math makes it seem. In in the actual problem, like with the math, it slides down with ease. The rate never changes, but in real life, it's kind of hard to just replicate that, and that's kind of what it says in number 3. Plus, I pulled it too, so it's not even the floor. I could have pulled it at a different rate and changed it, so that also causes like inaccuracies. And the last part is that y is always change, or the rate of y is changing always. As it slides down, it starts decreasing at a higher rate. So um, what I used to calculate in the first one is I went by 6 inches, and then I got the time at that point, which is 0.51 seconds. That's how long it took to get there. And that's what gave us negative 11.768. But if I were to use 12 inches instead, at that point in the video, it's at 0.62 seconds. And then when we divide that, we get negative 19.35. He's rounded to 5. So that just shows that the rate of y is not always going to be the same. So it's not going to give us the same that we get in the calculations because, you know, it's increasing all the time. So yeah, that's pretty much it.